So Reiji is going to talk to us about an artificial creature approach to the origin of acoustic communication. And like presently you have talk is 20 minutes, so 50 minutes for talk and 5 minutes for questions.
Okay. Okay, thank you very much for introduction. Okay, I'm Reiji Suzuki from Nagoya University, Japan. Today, I would like to introduce an artificial creature approach to the origin of acoustic communication. Okay, constructive and evolutionary approaches have contributed to discuss the emergence and evolution of acoustic communication, including human languages, because it is difficult to directly observe those processes from past materials. This study focuses on the hypothesis on the origin of acoustic communication, that is, acoustic communication in terrestrial animals started as noises that are contingent with breathing or gestures associated with predation or feeding, which then gradually ritualized, forming the fixed action patterns reflecting intentional or emotional states, which further led to the evolution of language. On the other hand, artificial creature approaches has contributed to understanding the co-evolution of morphology and the behavior of physically embodied agents. And then recently, this kind of approach has been extended to the framework for the interaction among ecological, evolutionary, and developmental processes, such as evo-devo related things, and also the eco-devo, such as niche construction. And also has been extended for the combination of in silico and in reality approaches for soft robotics. However, a few approaches have considered the emergence and evolution of communication channels themselves, originating from inevitable noise. So the purpose of this work is to consider this scenario from artificial creature approach by designing and implementing an evolutionary simulation framework for artificial creatures. In this framework, many artificial creatures can coexist, each interacting with each other in a physically simulated environment. Sounds are inevitably generated by the behavior of creatures in the environment, which are perceived by and possibly affect the other creatures. And morphology and behavior of artificial creatures can co-evolve. This presentation introduced this framework very briefly and reports on 3 initial experiments with different tasks. Okay, let me explain the model. We call this model EvoCreature. As you see, there are multiple individuals of artificial creatures like this, and each composed of several rectangular blocks connected with hinges in a 2-dimensional grid field like this. And they can make sounds when their bodies collide with each other or with obstacles. This includes the self-collision between body parts not connected directly like this, and also the collision with a field. You can see in this video some yellow lines like this. This represents that a sound is emitted at the corresponding location, and that volume is corresponds to the length of the yellow line. So you can see that the sounds are emitted here and there, while we cannot hear directly, but anyway, they are making sounds. And these sounds can be perceived by their auditory sensors. Each block can contain this kind of auditory sensors. This is an image. This sensors allows the agent to detect the direction of arrival of a sound source from the reference line. And also, the sensor can detect the volume. But the volume decreases as the distance from the sound source increases like this. Actually, the basic volume is determined by the relative speed between the colliding objects and the size of that object. And this figure shows an image of the genotype, and each agent has a genotype, and this is a directed graph and a simplified version of the Sims Brocchi's model. This represents a developmental process of phenotype graph like this. in this case, a tree-like structure. And this phenotype represents the physical structure of bodies like this. So the number of and the size of the blocks hinges between blocks like this. And this phenotype also represents the neural network inside each block that connects inputs from the several types of sensors, visual, auditory, contact, hinge angle, and the information from other blocks to the output. Outputs are the torques applied to the hinge connected to the another block like this. So the overall structure of the network creates sensory motor loops. And the evolution process is based on the simple genetic algorithm. I will skip the detail here. And today I would like to introduce 3 initial experiments in order to see whether this proposed framework can contribute to the understanding of evolution of acoustic communication originating from inevitable noise. The first one is aggregation task to see whether a collective behavior using inevitably generated sounds by others can emerge from a minimal task. The second one is a resource acquisition and sharing task to see whether the population can evolve to use both environmental and inevitably generated sounds by others in a simple foraging task. The third one is an acoustic niche separation task to see whether an artificial creature approaches to acoustic niche hypothesis contribute to exploring the origin of acoustic communication. By the way, this acoustic niche hypothesis has been recently discussed using some air-life approaches. So let me explain the first one, aggregation task. In this task, we assume 50 individuals in a playing field like this, and yellow line represents the initial position. And we assume that the initial population is composed of the pre-evolved individuals that have an ability to approach to a single sound source beforehand. Then each individual can receive sounds emitted by the other individuals, excluding the sound emitted by its own behavior. So each, for simplicity, each agent has a canceling mechanism of the ego noise. The fitness is simply the number of the other neighboring individual within the radius of 10 at the end of the simulation. So the individual will be more adaptive when the gathering more other individuals around it at the last time. And we also add some component for fitness, an exclusion of individuals who did not move at all to facilitate the behavioral pattern. This is an example result. It shows that the transition of the average fitness and the max fitness and total volume in a typical trial. This figure shows the population evolved to aggregate successfully because the fitness increased. And also see that the total volume also evolved to be small, meaning that for this task, there should be a necessary and sufficient amount of the volume of sound events. And this is the behavior of the best individual in this trial. And this video shows an example behavior of the population composed of clones of the best individual, but basically it's similar to the population in the last generation. And this figure shows the scatter diagram of the average sound volume of each individual on this population and emitted by each individual and its traveled distance, so volume and distance. And the size of the circle represents the fitness of the focal individual. So as you see, the individuals moving and making sounds actively tended to be more adaptive. And also, we can see that individuals moving not so much also became adaptive if they make sounds actively. So this means that these kind of individuals are leader and they gathered other actively moving individuals by their sounds. So in this case, the individual like this or around here can become the leader and others are follower like this. So we can see this kind of behavioral diversity in this kind of acoustic communication. The second one is the resource acquisition and sharing task. In this task, we assume that there are 4 resource blocks in the environment, and this is close to the sound source emitting a sound with a fixed volume to indicate the existence of 4 resources. So here's the acoustic landmark, and these are the resources. And around them, there are 7 individuals who are distributed circularly around the source like this. And the fitness of each individual is the total amount of acquired resource and a small bonus for the number of parts. For example, if there exists 2 individuals around this source, these 2 individuals share the total amount of these resources, 100, so the 50-50. Okay. And this is the result. This is an example transition of the number of individuals acquired any resources, and this is a variation in that acquired resources. So and this is a behavioral pattern in a typical generation. As you see, the population evolved to move toward a closer resource and stay around it. This leads to the equal sharing. And this figure shows that the trajectory of the individuals as the last generation. As you see that the individuals walk around the resources, 4 resources, and it's shared equally. But an interesting thing is that if we put this population, these individuals into the environment where no sound source, so no acoustic landmark, these individuals show this kind of a aggregation behavior. This implies that the evolved behavior in this environment could be executed for another adaptive behavior, aggregation. So last one is the acoustic niche separation task. We assume in this case, we assume the 2 species, A and B, and each consists of the 20 individuals, and each individual moves on a field without incoming sounds from the others for a fixed time step. And during this time step, they make sounds. And the frequency spectrum is calculated from the volume, but in this case, actually that the volume is regarded as signal strength itself. And anyway, the signal strength is transferred to the frequency spectrum using FFT like this. And we determine the main frequency value, that is the frequency at which equally divides the area of the spectrum power like this, half and half like this. And this value is averaged for the last 8 intervals. And the fitness of this individual is a difference in the main frequency from the average of the other species. So in this case, if this individual is from species A, this will be species B. So the individuals becomes adaptive when the main frequency has less overlap with the average of the other species. So realizing the acoustic niche separation. So this is the result. And this is an example transition of the average fitness and average main frequency. And this is a result over 1,000 generations. And as you see, the fitness evolved to be high for both in population, and also the average main frequency became different between 2 species like this. This shows the emergence of acoustic niche separation with different morphologies. Actually, so this is a movie of the example behavior at the last generation. So the red one is a species A, and the blue one is a species B. And as you see, and as for the species B, signal strength is like this, very slow sine curve-like pattern. So that this species generates the low frequency sound. Actually, this is a frequency spectrum, and there's a peak in the low frequency region. And also, as for the species B, this individual repeated the fixed pattern like this, and this is a high frequency spectrum. And the morphology is like this. And for the high frequency case, composed of the several blocks and the repeated rapid vibration. And as for the species A, they show that very small, slow waving like this. interesting thing is that this kind of acoustic separation is based on the different type of the morphologies. And also, I will skip the detail, but similar acoustic niche separation evolved in a 3-species case. In this case, that the main interesting thing is that the main frequency of one individual fluctuated in between 2 extremes of others. So high frequency individual and 2 low frequency individual. Okay, in conclusion, we introduce an artificial creature framework for origin and evolution of acoustic communication originating from inevitable noises. We conducted 3 experiments and a simple aggregation task to bring about diversity in the relationship among creatures, and the population could adapt to the combination of different types of sound sources in a foraging task. This yields the different collecting behavior as a byproduct. And the acoustic niche separation in frequency domain among species could emerge and bring about diversity in their morphologies, as well as behavioral patterns. While still preliminary stage, but we think that this kind of result shows that the potential of our framework. Thank you very much for kind attention.
Thank you very much, Reiji. It was a very interesting talk. I think that's the first time I see actually somebody trying to make sound from their own behavior.
Yeah,
it's
yeah.
kind of interesting. It's body parts.
Thank you very much.
Okay, so we don't have yet a question on the Q&A, so please write it down if you have a question. Otherwise, we will ask questions. Do you have a question, Manuel, or should I go?
I do. I actually do.
Okay.
I don't know if this is the right intuition, and so I'd like to ask you if this is correct or not. In your aggregation, say, phase, so here is the first figure, and then you had a slide about that, where you were showing like the fitness, say, like slowly going up. I'm wondering, like, is this similar in, at least, I don't know, like conceptually? You know, like the example with metronomes, like these things like going around, like say click, 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 and then you put, say, 100 of them, and then slowly they synchronize. Is the aggregation part in here, like in a way similar to this synchronization, in a sense that like through the communication, say, say the acoustic communication, these things actually synchronizing, and here synchronization.
Yeah, that's a very good question. Yeah, actually, this is actual behavior. So I think that they are not always moving. The point is that who will be the leader and who will be the follower in order to accomplish this kind of task. In order to that, to always doing the same behavior is not adaptive, because they move around always through the time, right? So that's quite interesting, but we needed to investigate in detail. But anyway, the interesting thing is that even in this kind of simple task, this kind of a behavioral diversification happened. And I think that the situation is a little bit more complicated.
Because, I mean, as you say, like you have this leader figure, like in the metronomes, they are all the same. Like there's no.
I see.
But in this example, they were all the same. They were clones, right? If I remember well. Actually, they were clones. So in this example, they were all clones, right? In the video you're showing.
Yeah, all close. Yeah, all similar. You mean?
Yeah, all the same genotype, basically.
Yeah. Actually, this is a clone of the best individual. But basically, in this type of simulation, that after the main generation, that the population is basically composed of a quite similar individual. So basically that's. But
you investigate how the leader come to be? Who is the choice of the leader in this case?
Actually, the spatial distribution might affect first of all, but actually we don't know who will be the.
Okay.
It depends on the.
Can the leader change over time?
I think that once we need to investigate in detail, but yeah, they are gradually getting together. So maybe sometimes making sound actively, but sometimes others take turns, or maybe.
I think I would have many other questions because I'm quite interested, but I think we have to move on to the next door. Thanks a lot, Reiji.
Thank you very much.
Thank you,
Looking forward
Reiji.
for what you're doing.